Welcome. Let's take a look at an example in which we will find the error in the volume of a ball bearing due to an error in measurement. We have an example, and here's an image of what a ball bearing looks like. The radius of a ball bearing is measured to be 0.8 of an inch. Assuming this measurement to be accurate within 1/100th of an inch, find the error in the volume of the ball bearing. So starting things off, the first thing I notice is that we're interested in the volume of the ball bearing. Now the ball bearing is a sphere, and the volume of a sphere is 4/3 pi r cubed. So that's the function that we will want to be focusing our attention on. And also we want to notice that it's indicated that the measurement of the radius of that ball bearing is accurate within 1/100th of an inch. That means that the error in the measurement of the radius could be larger by 1/100th of an inch, or it could be smaller by 1/100th of an inch. So the error in our measurement of the radius is within plus or minus 1/100th of an inch. So what that tells me is that my dr lies in this interval. That dr is somewhere between -1/100th of an inch and 1/100th of an inch. And so we'll want to be attending to this notion as we go through, and that's going to help us find this error in the volume of the ball bearing. Okay, so let's start by looking at the differential. So we know our formula for volume, so that means that the differential for volume, dV, is equal to 4/3 pi times 3r squared dr. And recall the role of this dr is it represents the error in the measurement of the radius. Now, as we look at our dV, notice that the 3's can divide out, and we end up with our differential dV as 4 pi r squared dr. Now, because we have these bounds for the error in the radius measurement, we know that our dV is going to be bounded, and it's going to have an upper bound and a lower bound. Now, if we were to measure, if we use our measurement, so if we use the measurement of 0.8 inches or 0.8 of an inch, we could say that we'd have 4 pi times our 0.8 of an inch radius squared times our lower bound for dr, and our lower bound is -0.01. And dV could be as small as that, or dV could be as large as 4 pi times 0.8 squared times our upper bound for dr. So because we know that the error in our measurement is somewhere in between -1/100th and 1/100th, then our dV is going to be somewhere between dV using our lower bound for dr and dV using our upper bound for dr. So if we multiply these quantities out, we get negative 0.0256 pi is less than or equal to dV, which is less than or equal to 0.0256 pi as our upper bound. And these are in square units. Now, just to give you a sense of how big these numbers are, this is approximately negative 0.08042 units squared. And this is positive 0.08042 approximately units squared. These are both approximations. But we want to focus on the exact values, but just to give you a sense of what that error in the volume is. So this represents the error in the volume. So let's go ahead and find the relative error. So since our dV, or our error in our volume, is an interval, we're going to explore relative error as a similar interval. So we need to look at this as dV over V is bounded below and is bounded above. dV is bounded below by 4 pi times 0.8 squared times negative 0.1 over the true volume of the bearing if 0.8 was an accurate measurement, which would be 4 pi times 0.8 cubed over 3. And then dV over V is bounded above by 4 pi times 0.8 squared times 0.01, or our upper bound, divided by the true volume, which is 4 pi times 0.8 cubed, all over 3. Okay. So what that simplifies to become, if I run this through a simplify, for example, I can see that I can divide out a 4 pi, and that's a 1. I can divide out 2 factors of 0.8, and I can do that on both sides of my, on the left and the right of my inequality, and so forth. And so when I'm done simplifying this, what I find is that I have negative 0.0375 is less than or equal to dV over V, which is less than or equal to 0.0375. So what we can say now is that the relative error is 0.0375, and we can say that the percentage error is 3.75%. And now what we want to do is use differentials to estimate how much the radius of the ball bearing must be increased to increase the volume of the ball bearing by 5%. So we want to increase the volume of the ball bearing by 5%, and we're going to do that through increasing the radius of the ball bearing. So we're trying to estimate how much the radius of the ball bearing must be increased, and notice that we are measuring the the increase in volume as a percent. So we will want to measure the increase of the radius of the ball bearing as a percent. So what we will want to do is compare. The increase in radius. We'll call that dr, to the original radius, which we'll call r. And we'll do this as a ratio so that we can determine the percent increase. To find the percentage increase. Okay, so we're looking at this comparison, dr to r. Okay, well, recall that our volume is 4/3 r pi r cubed. Let me get that pi in there first. Our volume is 4/3 pi r cubed. And that what we want to have happen, we want the change in volume to be 15, oh, my apologies, this should be 15%. To be 15% larger than it currently is. So the current volume of the sphere, or the ball bearing, is 4/3 pi r cubed, but we want this to be 15% larger. So we want the volume to increase by 15%. So this expression here, volume by 0.15, represents the change in volume being 15%. Okay, now, so we have this notion that we want our volume to change by 15%. We also have our differential. Our differential, if we apply that to our volume formula, is 4/3 pi times 3r squared dr. Note that our 3's will divide out, and we end up with our differential being 4 pi r squared dr. Now notice we have two different expressions or equations that describe how we want the volume to change. And note that we want them both to be valid. So what we're going to do is we're going to set these two equal to each other. That is, we're going to have 4/3 pi r cubed times 0.15, which is equal to dV. And that also has to equal 4 pi r squared dr. So in essence, we end up with just 4/3 pi r cubed times 0.15 equals 4 pi r squared dr. Now keep in mind that we're interested in finding this percentage increase, this dr over r. So let's take this equation and rewrite it so that we have that ratio. So for example, I can divide both sides of the equation by 4 pi. And when I do so, the 4 pi's will divide out. And keeping in mind that we wanted to end up with dr over r, I'll want to divide the r cubed over to the other side. So r cubed, that will divide out. And r cubed. So when the r cubed is divided on both sides, I end up with a dr over r. And so at this point, looking at how things have simplified, I've got 0.15 over 3 equals dr over r. And 0.15 over 3, if I simplify that, that becomes 0.05 is equal to dr over r. So what this tells me is that the relative change of the radius is 0.05, but the percentage change is 5%. So what we would say is that the radius must increase 5% for the volume to increase by 15%. I hope you find this helpful.